Hi, I'm Pavel. I work in Google in the optimization teams. And today I'm going to talk about various combinatorial optimization that happens at Google, both from the tooling perspective and practical perspective. I'm going to assume that I suspect that you know this company, so what it does. So I'm going to skip the company introduction and just go right into it. So I think at this point it's like the second to last talk in this whole summer school. So I think that I don't have to convince you that combinatorial optimization is everywhere. And if you look at the companies such as Google that does sort of like computer systems for a living, it's really at every sort of level of the stack of the technology that we have. So optimization is used to design hardware, to build the hardware through supply chains, to optimize the operations of the hardware in our data centers, then to optimize how the software runs on this hardware in our backends, and then even in front ends, there's a lot of optimization happening, like how to lay out the windows and stuff like that. So really, optimization is everywhere. So that's good because there's a lot of work for us. And just to jump in right into the outline for this talk, it's roughly split into two parts. First, I'm going to do a bit of shameless advertising of the library called OR Tools. This is the library for many different combinatorial optimization problems that our team develops for, I think, more than 10 years now. And in particular, I'm going to talk about three, let's say, recent or less recent developments. PDLP, which is the large-scale LP solver, CPSAT, which is the constraint programming solver, and MathOpt, which is our new layer to model and unify sort of the API across various solvers. And then I'm going to sort of a bit switch gear and switch into the topic of, yeah, how does it look like to work on an optimization project at Google? And a lot of the sort of things that I will be hammering on are very similar to the things you've heard in like last two talks. I really enjoyed them, and yeah, you will see it's basically the same points being reiterated, I think. So OR tools. So these are just sort of links you can see for yourself. Somebody of you have laptops that you can do it immediately. OR tools is a library of many different algorithms to basically solve four types of problems. So there is one is the linear programming and mixed integer linear programming problems. The other one is SAT and constraint programming. The third one is vehicle routing problems. And the fourth one is some kind of generic graph algorithms like flows and the shortest paths and so on. We have bindings to four popular languages. Like all of that is implemented in C++, but we also expose APIs to Python, C# and Java. We implement a lot of the algorithms ourselves. So we have solvers for LP. So like BLOB is the simplex algorithm. PDLP is the new large-scale LP solver I will be mentioning later. We have our own graph algorithms. Yeah, CPSAT, VRP. This is all developed in-house by Google for the last 10, 15 years. And we have two wrappers around those solvers. The new one, MathOpt, which I will be talking about as well, and the old one, a bit, I would say, simpler, maybe, MP model. So if you go to the documentation side, all of that will be sort of, hopefully, well explained there as well. So let's go and jump into the recent developments that Google have done. So the first is PDLP. This stands for Primal Dual Hybrid Gradient for LPs. This is the brainchild of David Applegate and his colleagues. And this is really like I would say, the largest scale LP solver currently available. Just received a very prestigious award for all of this work. And just to give you a notion of how big these LPs that we can solve are, the team has sort of experimented with solving something around up to 100 billion non-zeros in a distributed version. The PDLP takes a very different algorithm than simplex. Because of that, it's sort of like it's more approximate-like, but still at this scale of LPs, there is nothing else that can actually handle this kind of problems. And just to give you an impression of what was sort of necessary, so like, yeah, what you can't see here because there is an overlap, it's that there are two sort of main components for the success of the solver: theoretical advancements that you can see, and top engineering. So basically what the team did, they took the method that was in the literature, so-called PDHG, primal dual hybrid gradient, and started to add extra features, extra things to make it tailored towards LPs. And on the right-hand side, you can see that with every new feature they have worked on, like restarts, some specific scaling, some primal weight adjustment, step size adjustment, and some specific pre-solves, each time they got like a better and better performance of the solver, so that at the end they can actually solve the majority of let's say relaxations of MIPLIP problems to a relatively sufficient error rate. All right, so that was PDLP. If you have huge LPs, I encourage you to try it. In our experience, it can handle LPs that no other solver could. The next one is CP-SAT. So CP stands for constraint programming, SAT stands for satisfiability solver. So CP-SAT is a constraint programming solver built on top of a SAT solver. And in a nutshell, it's like it's like integer programming solver plus some specialized nonlinear constraints. So it only supports integer variables, but it also supports some nonlinear constraints, and it's always exact. So it's the whole implementation is done on integer arithmetic. So we have, for example, cutting planes and stuff, but it's all sort of like we have integerized version of those. We also use LP relaxations inside, which are based on floating points, but these are used mostly as hints, and we don't use the solutions of the LP solver directly as a solution. So thanks to this, CP-SAT is always exact. In terms of constraints, so yeah, it supports linear constraints, but also a bunch of other ones. So one example could be like no overlap constraint. So this is used to model, for example, intervals in like scheduling problems. So you have your variables and you have some associated length of these variables. And then when the solver assigns values to these variables, it ensures that, you know, if you were to put those intervals on a line, they would not overlap. And there are a bunch of different constraints specialized to different kind of problems. And also linear constraints with so-called enforcement, which I think in the MIP lingo it's called indicator, which means that you can have a construct like this, that you have some Boolean clause and it implies this constraint on the right. And it's only implied if the Boolean clause is true. And actually the SAT solver, based on which the CP has been built, has like sort of like native support for this kind of constructs, which means that CP-SAT solver is extremely strong at, I would say, like Boolean implications and Boolean reasoning. So CP-SAT is, as any, let's say, mature math solver, a collection of lots of things. So the core is the SAT solver, where there is like close learning from infeasibilities, but there is also like this constraint programming layer with specific constraints and specific propagators for those constraints. There's also the linear integer part where we solve the relaxations, compute cuts, do pre-solves. There's a lot of heuristics, a lot of large neighborhood heuristics, and the recent addition of local search stuff, and it all works together. I think by default, it uses like 8 or 16 threads to sort of like try different techniques in parallel. And yeah, so as any solver, there's just a lot of inside. And I can say that, you know, CP-SAT is really the best solver, the best CP solver in the world. So for the past, I think 6 years now, there is this competition called Minizing Challenge for constraint programming solvers, and you can see like in the gold category, the OR tools, CP-SAT basically wins for the last like 6 years, almost in every category. And you know, CP-SAT is also a strong integer programming solver, linear integer programming solver. It doesn't support continuous variables, but what you can often, I mean, sometimes it's just not an issue because your problem is purely integer linear and you can just use it out of the box. And we have done this for some of the MIPLIP problems where we can close them much faster than other solvers. Like, of course, on average, the traditional MIP solvers are better. But still, there are instances on which, yeah, this is not the case. And in practice, for many mixed integer programs, you can actually rescale your continuous variables such that they are actually integer, and then you can start using CPSAT as well. And last component that I'm going to talk about is MathOpt. So this is our new sort of like layer to do modeling and solving in kind of like decomposed way, in the sense that like the portion that handles modeling is on one side, and it's sort of like detached from the solver side. So this is just a quick instruction how to get that using Python. And then, MathOpt separates modeling and solving. Sort of like the code looks kind of like that. You have like this natural looking constraints. So you instantiate your model, you add the variables, you add the constraints, you set up some parameters, and then you choose the solver you want. There are multiple solvers hooked up into this framework. So with just one line change, you can use skip, you can use Heis, you can use your favorite solver. And then, solve and get the result. So this is more or less what's currently implemented. MathOpt supports linear programming, mixed integer programming, quadratic programming, some kind of conic programming. It also supports non-linear constraints that are often supported by the MIP solvers, so like SOS, indicator, and so on. It also supports callbacks and incrementalism. And these are the solvers that are currently for which we currently implemented the interfaces in MathOpt. So yeah, a lot of features, a lot of solvers. You can really play around with that. One of the main sort of like design decision for MathOpt was to have very clear contracts so that when you switch solvers, you actually get sort of like the same thing. And there is like a strong contract on that, like for incrementalism, for example, that if you update your model and then solve incrementally, these updates of adding, deleting, or modifying variables or coefficients will always be in O1 amortized. So it's a very powerful tool to do incremental solving. And just a teaser, you can actually use this to solve remotely your models for free. We have like an alpha version of the service of MathOpt that you can sort of call from your laptop, and you can solve even just right now from this very room. You can send your model to Google Cloud and get the solution. So it would look very similar to what we had. You create the model, but then instead of like MathOpt solve, you use a different library called remote solve. You just need your API key to identify yourself, and this will basically, under the hood, send the request with your model to our servers. It will be solved there, and then you will get the solution, presuming it won't time out. So that's all about the OR tools, which is good because it's about half of the talk. So I've talked about OR tools in general. It's very versatile, very mature library. I would say it's really good for many different problems. And I talked specifically about the PDLP, CPSAT, and MathOpt. And now I will switch gears to more of a like, maybe even more interesting part for you. What does life of an optimization project look like? And throughout that, I will also emphasize why we like, for example, integer programming or constraint programming so much, why we like this, this technique to approach problems. So I will be showing this on example of like a hypothetical project that I perhaps took part of. So imagine that, you work at Google and you are an OR expert, and there is a team that develops a system to store and serve files, and they would like to optimize their storage. So it's like, it's more efficient. Let's call it like this. So they come to you and they say, oh yeah, we have these files. So these are these. We have to store them on machines, and we will be serving these files. So like a file is not really just bytes, but it consumes some CPU, some RAM, because we will be serving those files. So you can think of it as a multi-dimensional item. And then we have this containers, so these bins, which are just multi-dimensional containers, and we want to assign one to the other, right? So how to do that? So it's very easy to do it with MIP. First, what kind of things you have? You have items, you have bins, and you have multiple resources like CPU, RAM, etc. You have a decision variable saying that, okay, whether to place item I in bin B. This is just a Boolean decision. And then you have some input data, which is like how much resources are required by each item and how much resources are available. So what is the capacity of every bin? And then you just put it into constraints. So first, overall, for each item, you have to ensure that the item is placed. This is like it's not like a knapsack that you pack for your holidays that you can throw out some stuff. This is like a real life system that stores files of users. So yeah, the assumption is that it will all fit, right? The engineering team will make sure that the overall capacity of the system is such that it will all fit. So we can write this relatively safely. And then, of course, we have to ensure that it will fit in the sense of the resources, that no resource will be overconsumed. And if you have that and you run this, basically the map will provide you some assignment of files to containers. So you go back to the team and say, yeah, this is our solution. Then they say, okay, but cool, but yeah, this is real life system. Some files are hot, they are accessed often. Some files are not that hot, they are accessed less often. So we basically replicate the hot files, so we have some redundancy. So we now need your model to include the ability to place not only individual files, but like replicas of files. So you go back to your map, and it's very simple because you just have an extra input data, which is the number of copies for each file that you need. And then, instead of a binary variable, you have just a generic integer variable. And then instead of equal to 1, you just say equal to number of copies. And that's it, right? I mean, with just few line changes, your model now supports this extra feature of handling replicas. So, immediately the next day after, you go back to the team and say, hey, yes, I done this. They are very surprised that you implemented so fast, but happy. But then they say, yeah, but it's kind of dumb what you do because your system have placed all of the replicas in the same machine. I don't want that. I actually want to spread them because if that machine disappears, then all of the replicas disappear. I need some fault tolerance. So what I need is to spread the replicas across different machines. This is even simpler to include in this model because you just need to revert the change you made. Now go back to the binary variables, and this will implicitly sort of enforce that we will have at most one replica on each machine. So yeah, super easy to include. You go back and they say, yeah, better, but still dumb, because your system have put like 3 files on one machine and 1 file on another machine. And really what I want is some kind of load balancing. I want to have this equal across all of the machines I have. So, okay, you go back to your model. Now you will be doing something slightly more difficult, not very, but slightly. We introduce extra variables that will track the surplus of files with respect to how many files you would expect in the perfectly balanced situation. So basically what you add is constraints that here this sum is for every bin, so for every container independently, you sum up how many items are there, and then you subtract how many items would there be in the perfectly balanced situation. So basically all of the, how many replicas you have in total divided by the number of bins. This gives you the expected number of replicas per bin. You subtract the 2 and you upper bound by the surplus, which you minimize, and then this variable will denote how much you deviate from the perfectly balanced situation, and you minimize this. So you basically minimize the deviation. And on this example, I showed this using the number of files, but you can do this for the resource utilization. So you could do it separately for CPU, RAM, and so on. Many different sort of flavors of this kind of balancing feature are possible. So yeah, you implement this relatively quickly, you go back, and then the team that you work with is almost happy, but still not quite, because they say, yeah, we run your system and we notice that each time we run it, it actually produces a different allocation. Because each time they run it, the state of the system is slightly different. So like the computational path of the map solver will be different, and you will get a very different assignment of files to disks or to machines. But this is a live system. Everything, most of it is already somewhere. And it's just that we need to modify it slightly, right? So some of the files are sort of like fixed. They should not be moved. So what they want is to get a solution which is just tiny bit different from what they have, which is like reducing the churn of the system. There are many ways to do that. One of the simpler ways to do that is just to explicitly upper bound the number of changes, right? So this is like a XOR between whether the item was in that bin and whether it is now. And if this differs, it means there's a change, and you just upper bound it by some value. With this, you can sort of explicitly limit the number of changes your model introduces to the living system. So that's it. At this point, the team is happy. And what have just happened, like in like this 5 minutes, we have built multi-dimensional, multi-bin packing with redundancy of items, fault tolerance, load balancing, and churn reduction. And this is just so beautiful for MIPS because it's super quick to iterate and to add new features. And because it's declarative, because it's like math, it's super clean what is happening. Like the objective and the constraints are sort of like explicitly out there, and the team that takes the solution from you, that they will now maintain this code and it will live in their system, make decisions in their system. They are certain what will happen, right? It's not an ad hoc solution. It's really like a declarative kind of thing. So of course, this would all be for nothing if we couldn't solve those things, right? Happily, we have the MIP solvers, IP solvers, CP solvers that are nowadays very powerful. Like in our practice, they can really handle problems with up to hundreds of thousands of variables, which is useful in many engineering applications. But what if it's too large, right? What if it doesn't solve efficiently? And by solve, from practical perspective, I don't really mean prove optimality. We really don't care about that in 99% of cases. What I mean by solve is find high quality solution in the given time budget. So what if it's not efficient enough? There are multiple things that you can do to this model to make it sort of efficient in your particular case. And again, this will be just a handful of different techniques, not at all not at all. Yeah, it's not that not all of the techniques will be here, just some examples that I happen to like. You might like others. So first, I encourage you to find patterns in your input data. Perhaps some of the files are actually similar to each other. You don't need maybe separate variables for each file. Maybe you can group them and then sort of merge the items and then have a variable per this group. Maybe you can look at the like technical aspect, like simplifying some assumptions. Maybe your model was assigning files to disks, but maybe not, maybe it's enough to assign to machines, or maybe to whole racks of machines, right? So look at the problem and see how much you can simplify it to make it easier to solve. Maybe you can do both, right? If you do both, then suddenly, your whole size of your problem just is reduced dramatically. Maybe you don't merge. Maybe you actually are more heuristical spirit, and you just sort of like say, okay, I'm just going to subsample the variables, right? Not include all of the decision variables, but let's say 20% of them, which will still give enough of like flexibility for the MIP to find high quality solutions. But because the size is reduced, it will be faster. All of the techniques are heuristical in nature, so you lose some optimality, but from practical perspective, we really don't care as long as it produces high quality solutions which are usable in practice. And these techniques are often very easy to implement, and they are quite reliable because of that. So one sort of last hammer that I tend to use is some kind of decomposition, greedy decomposition. Like maybe you don't have to place all items at once. Maybe you can group them in batches, solve one batch, fix it, then solve another, and you have like a sequence of models. And now suddenly each model in the sequence is very small and simple to solve. So once you do all of that, so you modeled, maybe you had to use some of the tricks to make the model solve in practice. Now you are landing the solution in production for all eternity. So what usually would have happened is if you didn't use MIPS and you would want to solve a similar problem, you would have to implement the algorithm, right? You would have to implement the logic that does this allocation of items to bins while respecting various constraints, some kind of complicated, perhaps complicated algorithm. And at first, it might seem like a good idea because you would just have like, the input to the algorithm, what is the current state of the system, the algorithm computes the allocations and then the output. But what happens in practice in such systems is that across time, more and more features are being added, the system evolves, and suddenly you have more inputs, the whole code becomes kind of convoluted. If it's like a specialized heuristic, specialized solution, the whole code becomes kind of like spaghetti in the sense that there are many corner cases, and it's very difficult to reason what happens under all conditions. And this is why we like MIP so much, because it decomposes. It's like it creates this isolation between the business logic, which is in the model, and between the number crunching, what happens in the solver. So this is why we like it so much. And you land that. And when you do that, what happens is that you have your real life system. So maybe this file storage and serving system. And to sort of make it run across time, you iterate through this loop that you take a snapshot of the system to know what is the current state. You run the model to optimize some parts of the system. And then you have the update, which you apply to the system. And if you are a big company, you have many such systems that talk to each other behind the scenes. And what happens is that you have multiple optimization models optimizing various systems across all of the infrastructure. And it basically proceeds like that. You could look at this as kind of like large neighborhood search, like on the real thing, right? Like because you optimize different parts in this smaller loops. And this is quite reliable because this is first doable because you can you optimize some things that you can actually do, and it just basically works nicely because it's separated, it's isolated, so you can test all of that in isolations. So that's that. Thank you very much.